is going to talk about a quasi-Monte Carlo data structure for smooth kernel evaluation. Okay.
Thanks, Andrew, and thanks to the organizers for organizing the workshop. I'll talk about joint work with Moses Charikar and Michael Kapralov. I'll describe all the things in the title, and I promise that underlying there's a sparsification result. Okay, so I wanted to start with an application that I think it's a really cool application of the kind of ideas that I'll be discussing. And it's this notion or this code of t-SNE. So maybe by quick show of hands, how many have either seen or played around with t-SNE? No? No one? OK, so t-SNE it's one specific optimization problem which is used in order to visualize high-dimensional data sets. OK, so I'm going to describe the problem. If you want, you can also play around with this website. What does it do? You give it as input a set of vectors, of high-dimensional vectors, something like R to the 200-dimensional space. And it's meant to output a visualization of this R to the 200 in, say, R2 or R3. Okay, it's supposed to help people see like if there's clusters in the data, or this is very, very popular. But I want to tell you about how it works, because it's related to the algorithmic task we're going to talk about. So how do you perform this visualization? Remember, the output is the location of these points. So it's an optimization where it tries to find where these n dataset points are going to lie. So how does it work, or what is the problem? Well, whenever you have two sets of points in the high-dimensional and in the low-dimensional space, what you're going to do is you're going to draw, I guess, what I'll call a geometric graph or a kernel matrix. And all this is an n by n matrix, which is going to measure some pairwise interactions between pairs of points in your data set. Okay? So for this talk, or for right now, we'll kind of grow in complexity with these kernel functions. You should think of a kernel function as a function which maps two vectors to a number. And in this talk, this number is going to be between 0 and 1. And this number also only depends on the distance between the two vectors. Okay, so the way that two dataset points interact is just merely through their Euclidean distance. When the 2 points are on top of each other, when they're exactly the same point, the kernel value evaluates to 1, so it has like maximum interaction. And as the distance between these vectors grows, the kernel value goes down to 0. It's supposed to model the fact that far away points interact less than, say, very nearby points. Okay, so just as a few examples, and some examples that will show up in this talk, this is the two specific examples of kernel functions, or ways to measure these pairwise interactions. The first one is the Gaussian kernel, which I wrote up here, just in case you forget. As you can see, it only depends on the distance between the two vectors. And as the distance grows, the quantity decays to 0. And this is the two-student or the t-student kernel. It's where t-SNE gets its name. The kernel function, it's 1 divided by 1 plus the squared distance between the vectors. It also is 1 when the distance is 0, and it decays to 0. But it decays at a much slower rate. Right? The decay is since polynomial in the distance between the points. And that's what I'm going to call smooth. Okay, so essentially, the decay of this function as the distance grows, if it's polynomial, that I'll call smooth. If it's not polynomial, like the Gaussian kernel, that will be not smooth. Okay, so what does t-SNE do? So t-SNE tries to find the locations by thinking of a fixed kernel function and writing down the kernel matrix in this high-dimensional space, writing down for any particular location the kernel matrix in the low-dimensional space. Now, it could be the same kernel, or it could be a different kernel. And then you try to find the locations of these points such that these two matrices are as close to each other as possible. Okay, so that's the optimization over these points with respect to some ways of measuring distance between these two matrices. Okay, good. Now, when you look at the code to actually run t-SNE, there's two parts. There's the part that deals with the high-dimensional space, and the part that deals with the low-dimensional space. And if you look at the part of the low-dimensional space, doing the computation of finding these locations and working with this low-dimensional kernel matrix, this part is extremely efficient. And really because in R2 or in R3, you're kind of at the comfort zone of two fields. On the one hand, computational geometry, where we know how to partition these spaces in KD trees, things like ball trees, and also scientific computing, which is really good at understanding how do we work with pairwise interactions. If you've heard maybe the fast multiple methods or n-body simulations, where you say, okay, you have a set of particles, they each interact with each other, and you want to be able to compute these interactions efficiently. However, if you go to the high-dimensional space, the t-SNE code that's actually being used, they currently just explicitly work with this n by n kernel matrix. And this is what makes t-SNE extremely slow. So in doing so, there's an inherent blow-up in the complexity, because the input size is n times d. It's n data sets in some d dimensions. However, when you write down this matrix, you pay an n-squared factor. OK, so what I'm going to talk about in this talk is one specific problem of working with these kernel matrices in high dimensions and how you can incorporate tools from TCS, things like locality-sensitive hashing, sketching, random projections, and so on, in order to speed up the computations in the high-dimensional space. OK, so let me define this one kernel density problem. That's the algorithmic problem we're going to be dealing with. And if you like to think about graphs, this would be like estimating the degree in this geometric graph of all pairwise interactions. OK, so what's the problem? That's the KDE problem. It's a data structure problem. So you receive as input a data set. This is my initial set of points in RD. And the goal is for you to produce a data structure, so to arrange these points somehow into memory, such that in the future, a new point is going to come in. That's the query. Now, you may have seen this point. It could have been part of your data set, or it could have been a point that you had never seen before. And your goal is to compute what is the net interaction of each data set point to that corresponding query. I'm going to use this notation KPQ. And you want to do this approximately up to 1 plus epsilon approximation. OK, so just concretely, KPQ is just the average contribution for each data set point, the kernel value between P, this is coming from data set point, and the particular query Q. OK. Throughout the talk, I'm going to call the value that you're trying to approximate this unknown quantity that you want to output mu. OK, this is the notation we'll use throughout the entire talk. OK. Any questions so far? Problem description clear? If you think about this matrices, you're trying to estimate what is the sum of the row or a particular column in this high-dimensional kernel matrix. OK, so this is the data structure problem. In its core is just summing up a big sum of n numbers. So there is a trivial n times d query time algorithm, which simply stores all n points. And then on a query, it just goes through all the data set points, computes the interaction, and takes a sum. Now, the reason why I draw this picture is another way to visualize a problem. You can think of the data set points as the peaks of these mountains. Each point induces like some kernel field, which decays as you move away. So when you take the sum of all these kernel values, you end up with some landscape. And the algorithmic problem can be visualized as that of approximating the value at any particular point. OK, great. So I want to tell you first about two different approaches for beating this n times d query time. And both these approaches are going to use the approximation factor and also use the fact that you can design randomized algorithms for it. And then our work is going to be how to get the best of both worlds for both of these approaches. OK, so I'm going to describe the approaches by comparing to the performance of a uniform random sampling. So suppose, as a first benchmark over linear time, you wanted to just take a random sample of points and use those points in order to approximate this kernel value mu. it turns out the number of points you would need for a multiplicative 1 plus or minus epsilon approximation is order 1 over mu times epsilon squared. Okay, now I want to make a remark, because every time I start working on this problem, maybe something that's kind of bizarre is that we're going to parameterize the complexity of the algorithms in terms of this unknown quantity which we're trying to estimate. Okay, so all the complexities are going to depend on mu, and mu is the quantity that you're trying to output. This feels a little bit bizarre at the beginning, because when you write the code, you don't know what mu is going to be. If you don't like this expression, you can think about setting a lower bound on mu, something that's some additive error that you're allowed to tolerate. Okay, so there's two main approaches to improve upon the complexity of uniform random sampling. They're completely different approaches, and they each focus on a different parameter to improve upon. So first, there are these approaches of what I'll call LSH sampling, and this was maybe pioneered in this work of Charikar and Simonolakis. They showed that, well, if instead of uniform random sampling, you came up with a different sampling scheme, you could improve upon the dependence on mu. Okay, so concretely, they showed that in a large generality, they can get 1 over square root mu epsilon squared query time. And then shortly after, there was this other work saying that for these specific smooth kernels, kernels which decay at a polynomial rate, you can improve on the dependency on mu even further to polylog 1 over mu over epsilon squared. Okay, these are the LSH sampling, and we're going to see a little bit more of those in a second. On the other hand, there's this other work of Phillips and Tai, which use a completely different approach in order to improve on the dependency in epsilon while keeping the same dependency on mu. Okay, so these techniques work by building core sets through discrepancy theory, and they achieve query times which are 1 over mu times epsilon. So linear dependence on epsilon, but still linear dependence on mu. And our work is going to show how to get the best of both worlds. For smooth kernels, we're going to obtain dependence on mu, which is polylog 1 over mu, the kind that we saw here in these LSH sampling approaches, while at the same time obtaining a linear dependence on epsilon. Okay. Now, the fact that we only work on smooth kernels, you'll see it's a limitation of this work. And one of the open problems is going to be to get analogous improvements over this with a linear factor in epsilon. That's something that our currently techniques can't handle. Yeah.
When like this inverse dependence on mu is coming from the fact that basically if I give you a point which is very far from the data set, like it doesn't capture my static set of data points, or it cannot be explained, then I'll have a bad estimation of the kernel value, because it's none of the points are kind of close to this.
Yeah, so I'll draw a picture in a second that'll clarify why for uniform random sampling you would pay a 1 over inverse mu dependence. And this will be in the next slide, I guess. We can talk about it. I'll first just briefly tell you why uniform random sampling, or in general what these LSH sampling approaches do, and why they can get an improved dependence on mu. And essentially what they do is they build an unbiased estimator for this unknown quantity mu. And then they use either Chebyshev or Chernoff bound to upper bound the variance of this estimator and give a finite bound on the number of samples that you need. Now, whenever you go through this approach, a 1 over epsilon squared dependence is somehow inherent. You know, when you apply Chebyshev's inequality and you're trying to get a multiplicative 1 plus or minus epsilon approximation, the additive error you can afford is epsilon times mu. So if you apply Chebyshev's inequality, you're going to get a 1 over epsilon squared. That's where the epsilon squared is coming from for all those works. Now, the following situation could happen when you're doing uniform sampling. It could be the case that your data set looks like this. There's a mu fraction of the data set whose contribution is, let's say, 1. Okay, so they're all on top of each other. The remaining 1 minus mu fraction is really far away. Now, this shows that if you don't sample 1 over mu, you're very likely going to avoid this cluster altogether, and you're going to be outputting 0, whereas the value was mu. Does that make sense? Does that answer your question? Yeah. OK, so what was the main idea of LSH sampling is that, well, you could try to do some kind of importance sampling to realize that really there was your query, and there were a bunch of points which contributed a lot. You would hope to sample these with higher probability and thus decrease your variance. So the main idea is, why don't we apply, say, locality-sensitive hashing, some kind of partition of the entire space, and then take a sample from that part. So when you take a query, you look at where the query lies, and you sample a point from that hash bucket. This intuitively is more likely to sample the nearby points. And it turns out analyzing these schemes carefully is what gives you this improved dependence on the variance. But remember, the epsilon dependence is just coming from Chebyshev's inequality. That one is kind of unavoidable if you're arguing via this method. OK. The other approach is how do you use discrepancy theory in order to build these core sets? And core sets is kind of similar to some sparsification of the data set. The goal in this paper of Phillips and Tai is to say, if you give me a data set, I can find a collection of points. These are important points. They're not done randomly, but they're after running a specific algorithm, such that the output of the kernel value just on these points approximates that of the original. This is the task that they're gonna study, but they do need one more assumption on the kernel value, on the kernel function, and that's that the kernel is positive semi-definite. OK, so I'm just going to spend a slide or two defining what it is, the context that they're working in, and how they can improve on the dependence on epsilon and completely avoid using Chebyshev's inequality. OK, so first of all, what is a positive semi-definite kernel? Or what makes a kernel positive semi-definite? It's the fact that, well, if people have heard of the word the kernel trick, all this says is that a kernel is positive semi-definite if you could have thought of an embedding, phi, that takes your points, it maps them to potentially some infinite dimensional space. But once you've mapped in the infinite dimensional space, the kernel value is exactly the inner product of the points after having applied the embedding. OK? So under this assumption that the kernel is positive semi-definite, in fact, both of these kernels are positive semi-definite. And many times when people talk about kernels, they really just talk about positive semi-definite kernels. Phillips and Tai show how they can run a kind of sparsification technique in order to decrease their data set. So I'm going to describe how that works, because that's what we're going to improve upon. In particular, they ask, how do I take my data set? How do I decrease my data set by a factor of 2? And they notice that this really corresponds to the following vector balancing question. So remember, we can always think of the data set points in the original space as having applied this potentially infinite dimensional embedding and working with inner products after this embedding. So what is the vector balancing question? You get as input this data set, or you can think about these embedded vectors. Your task is to find a setting of signs, one for each data set point, A1 through AN, such that for some unknown query, some point that you haven't seen so far, if you look at the sum of all the points which you've assigned sign 1, and you look at the inner products between the points that got assigned 1 and the embedded value of the query, remember, this is just the kernel value between Q and the data set point PI. That quantity, that inner product, is as close as possible to that same quantity for all the data set points which you've assigned -1. OK? Now, if you can do this, then this is really good for your halving technique, because this means that the sum of the kernel values on the things which you've assigned 1 is very close to the sum of the kernel values of all the things that you've assigned -1. This is the partition of the points, and you can pick the one which is smaller and use that in order to estimate both. Okay? So you've done one step of running this vector balancing question and decrease the data set by a factor of 2. What do you pay? You pay an additive error proportional to how small discrepancy you can achieve. What Phillips and Tai show that is essentially a black box application of t-SNE that we're going to see in a second, shows that you can always run an algorithm, a discrepancy minimization algorithm, to get a bound of some polylog factor. So now when you're using this technique, you can ask yourself, how long can I decrease my data set by a factor of 2 such that the average value is preserved up to an additive error of epsilon mu? So now, just to go through the application, you've shown that you can partition the points into 2 parts such that the sums of the kernel values are the same up to 1. Okay? But you're interested in the average. So you take 1 and you divide this quantity by the dataset size. So the additive error that you pay for 1 step is 1 over the dataset size. You can afford to do this so long as your dataset size is larger than 1 over epsilon mu. Okay, that's the analysis. Okay, so what was our main idea? I say idea with a question mark. Can we do the same thing as before? Can we just, in a very rough sense, apply locality-sensitive hashing and then run the discrepancy minimization algorithm, assuming some geometric assumption that we get from the image of a locality-sensitive hash function? Yeah. Yes. Yeah, so we'll see those algorithms too. Okay, so that's roughly the plan. Can I use some tool like locality-sensitive hashing or some random projection such that I partition my space? This gives me a geometric assumption of the points I'm working with. Now, if I run through the embedding and run through discrepancy, I would get a better bound on the discrepancy. This would allow me to decrease my data set even further. Okay. So we're going to improve on this algorithm. So I wanted to just give you the very basics of discrepancy minimization to give you an intuition for what is the right quantity that we need to optimize if we want to improve on this bound. So I'm going to do this by going through the simplest positive semi-definite kernel, or the simplest kernel, which is realized as an inner product of an embedding. And that's just a linear kernel. I don't do anything to the embedding. Okay, so now my kernel function is just x transpose y. And even more simple, we're going to be in one-dimensional space. Okay, so the kernel function between x and y is just the product of x times y. What is the vector balancing question that we're seeking? The task is you're given as input n numbers. These are the data set points. Your goal is to find signs, a1 through an, such that you minimize the difference between the kernel values among the things that you've assigned 1 and things that you've assigned -1. Or essentially, you want to minimize the sum of q. Now, everything is a real number, so q times the sum I equals 1, ai times pi. Okay? Now, remember, you get as input the data set points. So you know the numbers p1 through pn, but you don't know q. Okay, q is going to come later. But I guess in this case, it just simply factorizes out, so it wouldn't really affect what discrepancy you can get. OK, so the picture is like this. These are the data set points. You're trying to find a setting of the signs which minimizes this quantity for some unknown q that you'll receive later. What is the best bound you can achieve? Well, if you don't know anything at all, and you just pick random signs, what would be that? What is it that happens? Well, this q value factors out. It's q. And now, because you're taking random sums of values pi through pn, you grow as a Euclidean norm of these numbers. So this would be the discrepancy that you can achieve if you just pick random signs for your settings a1 through an. But I claim that for this specific instance, picking random signs is really a silly thing to try. Okay, can someone see what the algorithm should be? Yeah, exactly. You essentially want to do some greedy balancing. Okay, so the first point comes in. You pick an arbitrary sign. It doesn't matter. Then the second point, you try to counteract. If that point was, if you currently were positive, you go negative. If you currently negative, you go positive, and vice versa. If you run this algorithm, you actually get much better error. You get error which is proportional to the size of q. That was the quantity that factors out. But now it's the maximum value of the pi. Okay, in particular, this quantity doesn't grow with n, whereas this quantity grows with n. Okay, that's where the discrepancy is getting the big gains. Okay, but that was for one dimension. What happens for general positive semi-definite kernels? Well, now the kernel is just the inner product of this embedding. The discrepancy minimization task, wherever I saw pi, is now phi of pi. And I want to find signs so as to minimize this quantity. Okay. Again, random signs would give you the analogous results that we saw in the one-dimensional space, but now the L2 norm in the high-dimensional space after applying the embedding. So the kind of error you would get from random signs would be the L2 norm of phi of q times this quantity that would grow, the L2 norm of the norms. But similarly, there's been a work in TCS developing the analogous versions of this greedy balancing algorithm, even for high-dimensional space. And the kind of results that you obtain on the error are the analogous things that you would from the one-dimensional space up to some polylog factor. Okay, so this is kind of a really nice result. You can run these greedy balancing mechanisms and get error, which is proportional to now the L2 norm of the query vector and the maximum L2 norm of these PIs. Okay, so you can, if the PIs are small norm, you can play them off against each other. Yeah.
Is the log in n or is it in the dimension of the
It depends on which of the two algorithms you use. This algorithm, the self-balancing walk, is a very simple, really beautiful algorithm. It loses a factor of n. I believe this Gram-Schmidt walk is a little bit more complicated algorithm, and it loses a factor like square root log. I'm not exactly sure. Yeah, but we really don't want to lose log in the dimension here, because this could be infinite. That's a problem. Yeah. Good.
Yeah. Can you say anything about the running times of, let's say, the self-balancing walk? Like,
The self-balancing walk is a super simple algorithm. So you start with one point, and you do the analogous thing. You keep a running sum of where your vector is at. A new vector comes in, and you say, if I assign it 1, do I get further away from 0 or not? And depending on how much you correlate with that point, you set a random, you do this like random greedy thing that always tends to bring you back to 0. Yeah, this is really nice paper. Yeah. Any questions? OK, this quantity, which governs the error that we can achieve, is what allows us to then plug in to this halving technique. We pay an additive error with respect to this. And then the overall bound on the core set size is how many times can you repeat before you end up with too much additive error. It's directly correlated to how small this gamma 2 norm can be. OK, so just as a reminder, the gamma 2 norm of a particular kernel matrix K is given by, well, you can find the best embedding. And after you fixed an embedding, the worst two vectors take the L2 norm of the query vector and the L2 norm of the worst data set vector. That's the error that these discrepancy minimization algorithms will find. OK, so now very quickly, we can see the argument in Philipson tie that you can just use the positive semi-definiteness of these bounded kernel to get an upper bound on this gamma 2 norm. Why is that the case? Because the gamma 2 norm is just the product of the Euclidean norms of the query times the data set point. If you pick any point, the Euclidean norm squared is just the inner product with itself. But we set this up so that the inner product is exactly the kernel value. And the kernel value of a point to itself, the points on top of each other, that's exactly 1. Therefore, every single norm here is 1. Okay. That's the Philipson tie analysis. OK, so that takes us to our question. What if we could decompose a data set efficiently? Start out with this data set in d dimensions. You partition it up in an efficient manner, something like locality sensitive hashing, things that we can afford to do in a bounded running time. And then for each part, we tweak the embedding to show that if we ran discrepancy algorithms on the assumption that you now have a fixed geometric region you're looking at, that you would get smaller gamma 2 norm. Okay, that's going to be the plan. Let me just tell you concretely what we show. We show that suppose that the points that you're working with, the queries and the data set points, fall in the following geometric arrangement. There's going to be a ball of radius r, and the data set points are outside in this region of the ball B, and there's an inner region of a ball A. Okay, so we have a ball, and there's going to be an empty shell. If you take a positive semi-definite matrix and a positive semi-definite kernel, you're promised that all the points corresponding to the columns of your matrix, your data set points, are in this outer shell. And your query, all things coming from the rows of this matrix, are in this inner shell. And you found some bounded separation. You can guarantee that these points are separated by a shell. Then you can improve on this gamma 2 norm. You can find a better embedding where the gamma 2 norm of this embedding is going to be proportional to the kernel contribution roughly at distance r times some quantity which gets better as you increase the size of your shell. The question is, how thick of a shell could I fit between my data set points and my query points? But if you find such a geometric arrangement, then you can tweak the embedding. And if you ran discrepancy minimization, you would get a smaller gamma 2 norm and hence a smaller error. Any questions on this? OK. So let me tell you how we do this and how we combine it with the data structure. So our data structure is going to work by thinking about the various scales at the various scales of distances that points may lie on. So we consider, say, a scale r. This means that we're trying to capture the kernel contribution of points which are roughly a distance r away from our query. Now remember, we don't know what the query is going to be. But what we can do is we're just going to try to sample one of these random balls and try to capture the points which fall in the geometric arrangement for which we can improve on the gamma 2 norm. Okay. So we sample this random ball. And this is this inner ball and the shell that's supposed to separate. And then we try to kind of get lucky. And in a sense, even though we don't know the query, we could hope that once the query arrives, because this ball was random, the query happened to fall inside this inner shell. And there's some separation of some points which we throw out. But then you have a lot of the points at scale r which are split by this shell. Okay. If you got lucky and the query fell inside, it got separated by a lot of points at scale r, then you can run this modified embedding, which gives you the smaller gamma 2 norm, run discrepancy minimization, and the halving technique so that you can capture the contribution of these points with a very small core set. Okay? So that happens at one scale. We need to do this at all possible scales. I mean, you repeat until you get lucky with enough points. So you capture all the points that you split at scale r. And concretely, what is the size of the core set or the query time of your algorithm? Well, if the aspect ratio of the points, say the maximum divided by the minimum distance is phi, you have log phi many possible different scales. For each scale, we're trying to capture all the points at that scale. So we're going to repeat log n times and show that for each pair of points, we get lucky with constant probability, such that after log n iterations, we have captured all the points at that distance. And then when you capture a point at that distance, you pay essentially complexity, which is the gamma 2 norm divided by epsilon mu at that particular scale. But if you remember the geometric arrangement, the gamma 2 norm was exactly the contribution of the kernel. So this contribution here cancels out. And we're left with the polylog factor times 1 over epsilon. Okay, so this we can remove the dependence on mu all the polynomial factors in mu. Okay. So more concretely, what does the data structure look like? Now we have a tree of these core sets because we're applying locality-sensitive hashing and only running the core set algorithm for the points which fall in that particular arrangement. So in one step of this data structure tree, we've sampled the ball. And then we look at the points which fall fully within the ball. And we assume, or we look, if the query falls inside the ball, then we've ran the discrepancy minimization algorithms against the points that were completely outside the ball. These we get to improve. So in some sense, this hashing scheme, Q was able to capture all the points outside, but not the points inside. Okay, then we're going to recurse on the points inside. On the other hand, if the query falls outside the ball, then it has captured all the data set points inside. We can use that core set in order to estimate the contribution inside, and we simply recurse on the points outside. Okay. The only thing that we're hoping for is that Q always avoids this shell. Okay, that's the case in which we can't make progress. Any questions on the kind of the sketch of the data structure? Okay, so let me get to the final point on why we need smoothness in our analysis. So I said that this scheme only works for these type of kernels, but not for these type of kernels. So there's an inherent tension between how efficiently you can navigate down this tree and how good of a bound you can get on gamma 2. The reason is that on the one hand, you want to ask yourself, how thick of a shell can I fit between a query and many of the data set points of a particular length? If you make the thickness of the shell too large, it's going to be very unlikely when you take a random ball that the shell happened to fall between the query and many data set points, and this log n factor would need to blow up. Remember, we're repeating this log n times because each one of these pairs succeeds with constant probability. So this would suggest that, OK, because you don't know the query location, your hope is to fix a random shell and get lucky at splitting many of the query and data set points. This would suggest that you want to make your shell as thin as possible so that it's more likely to split many queries and data set points. OK, so it turns out that what you can achieve if you're going for distances at scale r, you can guarantee with constant probability a shell size roughly r over square root of the dimension. On the other hand, the reason why a shell is useful is because if you can guarantee that a query is inside and a data set point is outside, and you have an empty shell, that means that you can certify a lower bound on the distance between the 2 points. You can guarantee that any data set point and any query point would be at distance at least r over square root d. This means that the kernel contribution can't be too big, right? Because the kernel decays as the distance goes along. You can guarantee the kernel value is small. Intuitively, whenever discrepancy minimization messes up, the mistake is only proportional to, at most, the contribution at scale r over square root d. Okay? The reason why you need smoothness is that you're trying to get error with respect to the contribution of distance r, but you can only certify a lower bound of the kernel contribution at distance r over square root d. Now, if the kernel decays polynomially, the difference between these two can only be a polynomial factor in square root d. However, if the kernel decays too aggressively, then the ratio between these two numbers could be incredibly high, and then our gamma 2 norm would kind of fall apart. OK, so let me just conclude with some open problems. Now, I don't think that one is necessarily doomed for non-smooth kernels or Gaussian kernels. But one really needs a new idea. In a sense, there's a trade-off between the geometric arrangement that you can support very efficiently and the bounds on the gamma 2 norm that you can guarantee. So the hope would be to find another arrangement, maybe not a shell, But some other shapes that you obtain, say, from other locality-sensitive hash functions in order to guarantee some separation. I think if you were to do this, the bound would have to be something like 1 over mu to the 0.99, something sublinear in mu, but a linear dependence in epsilon. That's one open problem. The second open problem is that even though these discrepancy minimization algorithms are efficient, they're polynomial time, they still take quadratic time. So if you really wanted to apply this specific algorithm to improve on t-SNE, you would be running it in like the pre-processing is slower, and you would lose the gains from the query time that you would get. So the other open problem is to increase the time it takes to run, to decrease the time it takes to run these discrepancy minimization algorithms. OK, so that's all.
I'm curious about the random ball. How do you pick the random ball? Just pick a random point and move the ball or something?
Yeah. So we pick a random point. So first you can bound, so you know the scale. So you know that you've covered all the points at a particular distance. This means that all your points are within distance, say, 2r away from each other. Then you pick a random point, and you pick maybe a random radius between r over 10 and 2r. And that's enough to, and then you fit the shell of size r over square root d. It's just really vanilla ball carving. Yeah.
Are you familiar with Peter Lepage's Vegas algorithm?
No. What?
It's a different. OK, I'm just curious. I was wondering how this compares with that. It's a different way of evaluating Monte Carlo with some kind of sampling method, perhaps different than the new ones.
OK. Yeah, I'd be curious to talk about it. Yeah.
OK, no problem.
If there are no more questions, let's thank Erik.